Could you describe a project that you're working on these days?
So the project I'd like to talk about today is one of our most active projects at the moment. It's about monitoring of large root beds. So this is happening in Australia, where we have these large animals that are flying, bats that are flying. They have a wingspan of more than 1 meter. They have between 700 grams and 1.2 kilograms heavy, so they can actually carry some significant payloads to sense their activity. And the project is important because birds of bats are native animals in Australia, and it's very little is known about the animal because they cover large ranges over the year. They have seasonal migration patterns. They travel all around thousands of kilometers in Australia. And so people would like to know more about them, whether their numbers are stable, they are under risk of extinction, or there's too many of them. They're also feeding on fruits, so they actually cause quite a bit of damage on crops, on mango farms and stuff like that. So people would like to study their feeding patterns to understand better how to protect the farmers. And third, they are an important lever for disease spread. So there have been a couple of recent outbreaks of Hendra virus, which spreads from flying foxes to horses through urine or defecation of the bats on the grass that horses eat. And then the horses get sick. There's a lot of animals that sort of died over the last few years. But what is even worse, the disease can actually spread from horses to humans. And it's a disease, it's a virus disease against which we at the moment don't have a vaccine, so it's very dangerous. And so we are working with biologists on this project, which is basically on a daily basis. The plan is to deploy up to 1,000 nodes.
Could you
Uh,
describe the hardware and the software used in the project before we get to the
uh-huh.
deployment?
So I actually have a node to show you. This is one of the tags that we put on that. So we put it around its neck using this strap, and it's just going to be sort of hanging like that. When they're flying, it's going to be vertical like that. And so we have you see the antenna, that's a radio antenna. We have two solar panels, one in the front, one in the back. We have a battery inside to recharge the node here. And then we have a PCB board with a whole bunch of sensors. So the important sensors in there are GPS, with which we are measuring the location of the animal. Then we have accelerometer, magnetometer to detect activity, so we can only sample GPS location, for example, when the animal is moving. We also have temperature sensor and pressure sensor. So pressure sensor is supposed to help us with the height of the animal, because GPS is quite bad in predicting the height, and the temperature is just for a basic environmental understanding of the animal surroundings. And then finally, we have a microphone, which was also has a purpose of detecting the activity of animals and sort of activity between animals as well. So interaction of animals. So
So, what kind of
the
software runs on these nodes?
the hardware is basically based around a very typical sensor node, sensor network node, similar to Telos B. So it's a small. We actually use a system on chip, so it's a small MCU with a radio embedded in a single chip. There was a Surf platform that people use using the same chip. So we are using just the standard sensor network tools to write a program for the nodes. We are not using TinyOS. We are using Contiki, and that's for the node software. Then the way how we get the so the way the deployment works is we take these nodes, we put them on the beds, we let them go. That's the last time you see the hardware. They fly away where they need to fly, and they sometimes come back to the so-called camps where they come and spend the day after they feed during the night. So what we also do is we deploy base stations in the camps that talk to these tags on the beds and collect the data that, for example, the traces as they are flying around in different feeding locations. So the base station, I don't have one here, but it's basically a similar node to this. So it would have the same radio, similar suite of sensors, and it's connected to a much larger solar panel because it's connected to a 3G modem through which we are sending data back to our backend server. The backend server is in our data center. It's basically a regular type computer, and we are basically just saving data there in a big database.
Yeah.
So for the software for the base station, it's also running one of the sensor network operating systems. We haven't developed a driver for the 3G modem on the sensor node. We actually connected it to BeagleBone, which is a small embedded computer, so that's running Linux, and periodically it turns on the 3G modem and sends data back to our server, so that's running just the standard C or Python or whatever you are on embedded Linux. And then the backend server is just running a RESTful API through which we are saving stuff in a database. We also have a visualization on top of the backend server. So the visualization is basically a website, and we are using JavaScript and the V3 library to do some nice interactive visualization of the data that we've collected or the nodes that are available. It's basically a Google Maps-based display. And the analysis finally, so when we do graphs and plot graphs for papers or for reports, we're mostly using Python to analyze the data.
Do you use matplotlib or something like that, or what do you?
Yeah, matplotlib to plot the data.
I see. So I had a question about these nodes that you showed us. Do you manufacture it there itself, or do you just design it? Could you just tell us a little bit more about how these nodes are made and deployed?
So unlike pure software groups, we have a great advantage in our lab. We have a hardware engineering team. Now these guys have been working on different kinds of sensor network projects for the last 5 to 7 years, so there's a lot of experience. So basically the hardware design was just handled by hardware engineers. It's an interesting actually project within our lab where the node that I showed you that's hidden inside the board.
Yeah.
It's a little customized board that's basically based off a generic board that I have here. This board that I'm showing you just has the system on chip and a standard suite of sensors such as temperature and microphone and light sensors. Some of them we use, some of them we don't. But it was basically that custom board for the BED project was a sort of custom design of an existing platform that's been developed and tested, both hardware and software, and that's shared across other projects as well. For example, we have another project where we're measuring gases inside animals, inside cows in rumen, one of the stomachs of the animal, to assess how much greenhouse gases are animals producing. So that's basically using the same type of node, just a different suite of sensors, which is a great approach in terms of hardware and software design, because really a large sort of module of functionality across different projects. So our development effort was a little bit shorter than what you would expect. We basically tweaked the design, the verified design, and then got a prototype back. We started with a two-board solution, which looked kind of funny. So you see there are two boards. The top board is the generic board that we reused. The bottom board contained all the extra sensors that we wanted to add. You can see GPS antenna here at the end, GPS chip here. So that let us test all the sensors the new sensors sort of in separation to make sure that everything is working before we make the manufacturing round of a new single board. And it was also much faster because, as you can see, the generic board has a lot of components on it,
Yep.
which is typically takes time and is also costly to manufacture. So if you make a mistake in the design, it gets up to be very costly. Whereas the additional stuff, you see, there is much fewer components.
Yeah.
So there's much lower risk, and we just connected them with wires.
Mm-hmm.
In terms of the base station design, it was fairly easy because we just basically used off-the-shelf components, so we didn't have to do any custom design there. A little bit, we designed a board for solar charging and for charging the batteries, and that's powering separately the node and the power-hungry embedded PC with the 3G. But I think if you look harder on the market, you could even find off-the-shelf components for that. So the majority of the development was on the actual tag.
Mm-hmm.
In terms of the manufacturing of the case, so you can see we have this cool case where everything nicely fits in.
Yeah.
So that's also we are using the capability that we have in our lab. These are actually 3D printed to fit exactly the board.
Yeah.
So everything fits nicely in. There is not too much space. When you close it in, it's nicely streamlined and doesn't have additional bulk that you don't need. Yeah. So it allowed us to minimize both the volume and the weight of the final design.
That's great. So these nodes are made and they're deployed, and the data starts coming in. Have you encountered any data quality issues? For example, maybe not all the data is what you exactly expected or even good, or how do you even know the data is good?
Right. So in terms of the data, I guess you can do sort of common sense check of the data once you deploy, so you know what sort of ranges of temperatures, for example, for temperature sensor you're expecting, or what sort of location from the GPS sensor you're expecting. There was also we had some sort of data quality or assurance control during the manufacturing process itself, where manufacturers that manufacture these new boards for us, they also run a test program. That in itself is only looking at the data, that the right data is coming from the chips. So it just verifies there is a communication on the bus, whether it's SPI or R2C or whatever. But it does check that manufacturer comes in and stuff like that. Once we deployed, so for testing, we did a lot of testing before we put it on the animals, just around the building, and then you can compare the temperatures that are coming in with the temperature forecast from the bureau, from the weather prediction websites. For the smartphone, we actually could record and replay human voice, so that was also quite easy to check that we're getting sort of the right data from the driver. And for the GPS, you can also see that it localized you in the building where you are. Now, in terms of data quality coming from the actual deployments, there are some outliers that we observe. Typically, we only detect these outliers if they are clear outliers, which means if the value that we are getting from the node is completely outside of the range that we are expecting it to be. For example, we had some GPS samples come back from the chip that were somewhere in Africa or whatever, and we know we are in Australia within a certain area, so we can easily discard that. So that's some basic algorithms that we're running to clean up the data. Another way how you could look at or detect outliers is you could look at the standard deviation of the values, and if it's higher than what you're expecting of the values as they are coming from the node. If they are higher than what you're expecting, you can try to do some look at the short, window, median, or mean of the values and find the outlier as a point that's far away from the mean. So at this point, we are only sort of using and looking at very simple analysis as we just started getting data from the nodes, but possibly in the future we'll look at more complex algorithms.
Mm-hmm. Great. So we learned a lot about the hardware and software platform and what the project hopes to understand, as well as some of the data quality issues you might encounter more as you start getting into data analysis. Now, finally, if you wanted to share any tips or insights about how to have a very productive platform on your desk, any programming languages, compilers, anything else you would like to share with our students?
Mm. So this project, as I mentioned before, was quite specific in that it's very constrained for the hardware and software developer, because once you put your platform on an animal, that's the last time you have access to it. So you can't really recover the node, you can't really inspect what's happening if there is a bug or whatever. You can't really debug it anymore.
Mm-hmm.
So what we found incredibly useful was to put in some checks and balances to make sure that the node periodically talks to you,
Mm-hmm.
even if there is a bug in the algorithm. So a great tool for these are watchdog timers or grenade timers
Mm-hmm.
that fire once your program gets in an infinite loop and doesn't tickle the watchdog. It will just reboot the whole node. We also are using a standard set of parameters that are saved in a flash memory that we never touch after implementation. So there is some basic core functionality that the nodes will always have.
Yeah.
The other thing that's incredibly useful with systems that you don't have access to is to be able to remotely inspect and reconfigure programs on the fly. So here we're just using standard RPC commands, and from a base station remotely RPC the node, get values of any sort of variables or change parameters, and stuff like that.
Yeah.
In terms of data processing and analysis, of course, Python has libraries for data analysis, starting with NumPy, SciPy, all the way through Pandas. In terms of visualization, for figures, Python quite good support Matplotlib, for example, for generating nice-looking figures.
Yeah.
But if you want to have some interaction from the users, it's typically we found it's very good if you can minimize the infrastructure that the users need to install.
Yeah.
So we just decided to go with the web interface,
Mm-hmm.
and there we just started working this year with JavaScript and D3 library.
Yeah.
And it's incredibly powerful, a bit difficult to organize your code around, so it's a little bit of a headache. But you get like really nice interactive website where you can like the ranges of the data, and out, on the fly, it's generating the data that the user wants to see.
Yeah, D3 is just an amazing resource. I've also started experimenting with it myself, and it's just amazing. Yeah. So, what do you have on your personal machine? Do you use Windows or Linux or?
Everyone in our lab is using Mac.
Uh-huh.
And most of us are also using a Linux computer to run stuff as well.
I see.
So many of the actually most of the scripts are, I think, running on a Mac server.
Okay. Mm-hmm.
But the development and everything is happening on a MacBook.
Okay. All right.
Now, there was one interesting point I wanted to mention about the database backend, which I almost forgot.
Yeah.
So we had a system set up in our lab where all the active SensorNet deployments would be feeding data to an Oracle database.
Mm-hmm.
Now, over time, that's grown too large and too inefficient. So we had really trouble doing interactive stuff because it just wasn't coping with the level that JavaScript was requiring.
Yeah.
So we actually ended up switching over to HDF5 file system, and which allows us to separate all the deployments to separate machines, or if there is an old outdated deployment, we can just save it as an archive,
Yeah.
as one big file. Tars even put somewhere on the server that we don't lose the data, but we don't have to actively support querying of the data any longer.
Right.
So, and that's been working. And also we moved away from just from SQL-like queries, with which we used to query data, to RESTful APIs,
Yeah.
which makes it very sort of elegant and quite a lot simpler as well.
Yeah.
To query your data, as you can sort of inspect through URLs, you can expect the structure and the hierarchy of your data.
Yeah.
So
Yeah.
that's been quite a good experience for us this year.
Oh, that sounds great. So most of the changes are due to more and more external scientists and customers wanting to interact with the data. Is that one of the reasons why you're moving to these architectures?
That's right. That's right. And the old stuff, one database fits all, was really cutting it in terms of speed. So you would click somewhere to get the data week, or even last day of data, and it would take 5 to 10 seconds to download that. Whereas now with the JavaScript, you can dynamically change the query that you have, sort of with like a bar, interactive bar,
Yeah.
across your timeline,
Yeah.
and it updates without you even note that there's some communication with the backend server.
Oh, that sounds wonderful. Are you planning to make any of this open source?
We'll see.
We'll see. All right. I hope you will release it as open source when you get a chance to work it out through your organization. So thank you for your time today. We got a chance to learn a lot about the project you're working on, as well as how you approach your project. So there are lots of things for us to learn from this experience. Thank you.
Not a problem. Have fun, guys.